examination. So hopefully that this can help you. Okay, if you got any questions, please do ask. Okay, so let's focus on the 2 through 3 paper. Okay, so quickly, okay, so we have this. The first one is a standard questions. Okay, to ask us about the SI and the base unit. Okay, SI base unit. Be careful about SI unit and the base quantity. So we have the base quantity here and we have the SI unit here. Okay, so base quantity, right? We have many quantities. Some are base quantity, some are non-base quantity. Okay, so base quantity we only have 7, and in 7 of them. Okay, but in your actually we have 7 of them. But in your syllabus, right, you only learn about 6. Okay, so don't care about the 7th. Okay, so we have 6. So how to remember all this quantity, right? I just use the picture to help myself. Okay, normally I just say that okay, Candy Crush. So I just use my very heavy handphone to run the Candy Crush. Then in the Candy Crush experience, right, actually you have all the 6 quantity out there. Okay, the first one is the length. Okay, because when you go to swipe something you score is actually like either 3 joules or 4 joules, the kind of things. Okay, so Candy Crush, right? So 3 candy or 4 candy. So that's length. Okay, so second one is actually the phone is being heavy. Okay, so it's being uh, is the mass of it. Okay, so the mass, the length, and the count. Okay, how many candy? Okay, so the count. These are 3 standard. Okay, so 3 basic quantity. I will call it base quantity, but 3 of them are very basic. It's just the length, the the mass, and the count. Okay, the fourth one is also very simple because you when play Candy Crush, you there's some timer taking, right? So it's time. Okay, so you have 4 of them. Okay, so 2 more. Okay, which is like why I'm choosing Candy Crush, because your phone is going to get hot. So it's actually temperature. The last one is actually your phone is running out of battery. So then we have electricity. Okay, so we have the base quantity, but each base quantity, right, we have many measurements, but only one guy is chosen to be the SI unit. Okay, so for length, we have meter. Okay, we have meter. Okay, for the length, we length. Okay, trying to get my pen. It's like that. Okay, anyway. Um, okay, so it's a length, right? We have meter. Okay, so we have meter for length. So time we have second. Okay, time we have second. Length we have meter. And then the count. Sorry, my mouse size is bad. Okay, so count we have mole. Okay, we use mole. Okay, all the weird stuff. Okay, because length we use meter, which is actually quite long. Only time is second is okay. Then the temperature you have is using Kelvin. We have degree Celsius. We don't want to use. Okay, all the weird stuff. And electricity, right? We do not care about the current. Actually, we care about the voltage. Okay, so potential difference. Okay, potential difference. We have the V. Okay, so the last guy will be 1, 2, 3, 4, 5, and the last one will be temperatures there. So 3 of them is the mass. Okay, so the mass is in gram. Okay, so only one guy we choose it in gram. Okay, so here this is the answer. Okay, so base quantity, weight is not a base quantity. We have the mass. Okay, and this is not SI unit for any quantity also. So both are wrong. Okay, temperature correct. We use Kelvin, correct. Okay, current we don't use current. We use potential difference or voltage. Okay, so V for V this is correct. Okay, so time we use second. Okay, so this is wrong. Okay, so only B is the answer. Quickly, which statement is correct? Okay, speed. Okay, so we have this is kinematic. Kinematic we only have all the quantity which is the distance or displacement, speed, or velocity, and accelerations. Okay, so we only have this. So we have those kind of quantity here. So which statement is correct? Speed is the scalar, velocity is vector. So vector has magnitude and directions, or rather the length and directions. Okay, so scalar have no directions and only have magnitude. Okay, so speed is magnitude with no direction is correct. Okay, vector has direction and have magnitudes. Both have. Okay, so these are all wrong. Okay, this is wrong. This is wrong. and this is wrong. Okay, so this is correct and this is correct. So it's B. Okay. One speed time graph. Okay, so graph, right? We only have two. Okay, one is a speed or velocity time graph. Okay, another one which is the distance time graph. Okay, distance or displacement time graph. Okay, so for displacement time graph, remember the gradient we have, right? The slope we have, the gradient we have is actually the speed. Okay, so how do we remember this? Actually, just use the unit. Okay, use a unit to do. So when you need to do the slope the time, you use the y value over the x value, right? Okay, so use this to divide this. So 20 divided by 2 is actually 10. Okay, so if you need the slope, is divisions, right? Division, so it's meter per second divided by second, you have meter per second square. Okay, so the slope is actually acceleration in meter per second square. Okay, and but the area on the graph will be the multiplication. This area times this area, okay, half time base time height, that kind of things, right? So meter per second times second, you get back meter. So this is why this is the displacement. Okay, displacement. So this area under graph is the displacement. Okay, so area under graph is displacement. So they're asking for a tennis ball when it's thrown directly upward from the ground level. Directly upward from the ground level. Initial speed. Okay, this is correct. So what do you want? You want the maximum height reach, right? So from the ground level, you throw the ball up to somewhere here. And if this is the graph, the initial speed is fast and slowly to slow, okay? And go to stationary. Okay, that's the maximum height go. So it go to 0, right? At the end. Okay, so that's what I mean. Initially the speed is 20. It's fast, okay? So 20 goes 0, but this is a speed, okay? So that's the total distance that you're looking for. So the total distance travel from here to here, okay? So from here, from the time you to 0 and the time to 2 seconds, so 0 to 2 seconds. So that's the area on the graph will become the displacement, the displacement that you have moved to the top, okay? So simply 2 times 20, half times 2 times 20 will be the triangle area, okay? So 20 meter, okay? Answer is C. Got it? Okay, fourth one, okay, airplane towards okay, so in this one we're testing on the dynamic, which is F equal to ma, okay. A is the accelerations, right? Okay, so A is the acceleration. So remember, even though A is something to do with velocity, but what caused accelerations? The thing that caused acceleration is F, okay, it's the resultant force, okay? So this is the resultant force. It's not any force, it's the resultant force. If resultant force means it's the overall effect of all the forces. Okay, and in your syllabus, right, you see all these things, but you can't do that. Okay, you only can do on any specific directions. Any specific directions. Okay. So if you talk about horizontal, we talk about horizontal. We'll talk about vertical, we'll talk about vertical. Okay. Since the airplane is actually having acceleration forward, means that there is an acceleration forward. There is acceleration forward means there is a resultant force forward. There's a resultant forward. If there's a resultant force forward, my forward force must be greater than my backward force. So I will have the thrust being greater than this guy, air resistance. Okay, the thrust is greater than air resistance. How about up down? Okay, vertically we don't have we say constant height. Okay, constant height means that there is no velocity, but of course there's no change of velocity also. So that means there's no intention of going up or down, can remain stationary. That means acceleration is equal to 0. Okay? When acceleration equals 0 means the resultant force is equal to 0. Resultant force equal to 0 means the up-down forces are balanced. So that when you so-called add them together, they will be added like a zero sum like that, okay, against each other. Okay, so that's why I have the lift equal to weight. Okay, these two forces are actually equal. Okay. So this force is greater than that force. Then got to give me a direction in this way with a resultant accelerations. Okay, resultant force to give me acceleration. So this is either these two are balanced or this is greater than that. Okay, so air resistance is balanced by the truss. Air resistance, no, is lesser than the truss. Air resistance is lesser than the truss. Air resistance balanced by the weight. Air resistance this way, weight is this way. So they are not on the same direction. Okay, so this is totally nonsense. The lift is balanced by the truss. The lift is balanced by the weight, so it's not the truss. Okay, the lift is balanced by the weight. The lift is balanced by the weight. Correct. Wow, this is also correct. Okay, so so wrong, correct. Okay, so the answer is D. Sorry. Okay, a rock is isolated in space, very far from any star or planet. A rock is isolated in space, outer space, very far from any stars or any planet. That means this rock is dangling around by itself. Okay, don't know what happened. Which statement about the rock is correct? The rock does not have mass or weight. No, the rock always have mass. So long as you have the atoms, you have the molecule, you have the particle, you have the mass. Okay, it's the amount of matters that you have. But the weight, it needs a gravity. Okay, so you need mg is equal to weight. Okay, so is when the weight is zero in outer space, it doesn't mean that your mass is zero. Okay, it can tell actually is your g is zero. Okay, there's no gravitational pull effect. Okay, so it has mass, certainly has mass. Okay, this might be correct, but it certainly it has mass. So does not have mass is wrong. Okay, so this sentence is wrong. The rod has mass but does not have weight. Okay, this may be correct because there's no gravity. The g is zero, but the m is a constant. Constant times zero. The weight actually is zero. Okay. The rock has mass and weight, but the weight is 1/6 of its weight on the Earth. This the weight is 1/6 weight of the Earth, right? That means the gravity is 1/6 of the gravity of the Earth, right? This is actually the moon. Okay, when you add the moon, it's 1/6. Okay, this sentence is weird. The rock has weight but does not have mass. This is totally nonsense. Okay, unless the rock does not have any particle, any atom, anything. Okay, so otherwise it have mass. Okay, and this depends on whether mg or g is it there or not. Okay, so in outer space, don't have any star, don't have any planet to influence that. That means the gravity is zero. So a rock is dangling there, so have mass and no g, so no weight. Okay, that's the answer. So blah 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 blah. Okay, B is answer. Okay, supposed to be a lot faster in this case. The four solid block blah blah. Which block is big of material that is greatest density? Density is mass over. Density is how density is mass over volume. Okay, mass over volume. Okay, so mass over volume density. Density normally you use a rho. Okay, very cheap kind of rho. Okay, density of mass over volume. So equal mass, right? They're all same mass, so it's all about the volume. Okay, volume is the length times breadth times height. So 1 times 2 times 2 is 4 cm cube. Okay, cm cube number I get 4. Okay, 1 times 1 times 1 is 1. 2 times 1 times 1 is 2. 2 times 2 times 2 is 2, 2, 4, 4, 2, 8. So it's 8, right? So same mass, and they want the greatest density. So I want the smallest denominator. Okay, smallest denominator, answer is B. Flat object lies on, so this is a piece of cardboard or such. Okay, so pivoted at point P. Like when I say pivoted at something, okay, I know in your syllabus talk about pawn, okay, but don't ever believe in what you hear. A pawn P means that actually is an axis that pokes through the pawn P. Okay, poke through the pawn P into the paper so that the whole piece of cardboard, right, can be swung around. And that's actually what it means. A force applied to the product to moment about the pivot. Which direction of force produces the greatest moment? Which direction of force produces the greatest moment? A force applied to produce a moment about the pivot. Which is, okay, force is, okay, moment. Moment is equal to force time perpendicular distance. Okay, how about this is not a very good question. Okay, so the idea is that a force applied, I think a force is the constant force. That means A, B, C, D assuming the same amount of strength. Which one will cause the biggest moment, means the turning effect. That means which one you can swing the hardest of the door. Okay, so it's actually 4 times force times perpendicular displacement. For any force like this, right, which is not perpendicular to the distance of the pivot, okay, we will need to resolve this force to two components. Okay, so one component will be this force will resolve with a perpendicular components and the parallel components to the axis between the point that you apply and the pivot. Okay, so anyway, when you need to resolve it, it will be a smaller effective component. So this one, right, parallel to the axis, right, will have no effect. Only this guy has effect. So this guy will ultimately be anyway shorter than A. Okay, so this is actually lesser than A. The effect of your force times perpendicular distance will not be the full strength. Okay, so this one also need to resolve like only this tiny components, right, is perpendicular to this axis. Okay, so this components will be useless for turning effect. Okay, so only this amount. Okay, so it's this value times perpendicular distance. Okay, also from here to here. So this less than A, this is worse than A, and C is totally useless because it's in the same line of the axis. So it's 0. Okay, 0 compared. So this one is perpendicular. So the length is the same for all the points, but the force perpendicular components, right? The whole force can be applied as a perpendicular component. So the D will be the strongest one when you do the mathematics force times distance. Okay, because only the perpendicular amounts can be considered. Okay, so force times perpendicular distance, or rather, you can also say it's the distance times the perpendicular components of the force. Okay, so just now I resolved the force to keep the perpendicular distance fixed. Okay, it's actually easier physically to be seen this way. Okay, if you can or want to do this, it's okay. Okay, you can also resolve the distance to a perpendicular distance. That means I keep this force, right? I keep the A, this force, okay? But I just say this is my perpendicular distance. Then I just consider this is the D amount. Okay, I can do that. Okay, and you see the D will still be smallest here and the longest here. Okay, and this is force where you walk through. Wow, close to this one, you only have a very tiny, small perpendicular distance. Okay, then or close to 0. Okay, so C also got nothing. Okay, B, you resolve it the force in that way. Okay, then you find the perpendicular distance only tiny bit like that. Okay, you can do that also up to you. Okay, for me, I fix the distance and do the perpendicular force. Okay, it doesn't matter. Okay, so largest moment. Okay, answer is D. Okay, got a question? Just ping me. Okay, anything. A ballet dancer balance on the toe one on the toe of one shoes. Just mass M and area of the toes is this. So what is the expression equal to pressure? Pressure P is due to force time over perpendicular area. It is just like the needle poke to your skin. You feel very painful because the area is very small. Okay, so pressure is actually how hard it press. Okay, so use a needle, kind of a very small area, a small amount of force actually can cause very great pressures. Okay, on the other hand, you use a whole palm, you can put harder. You also won't feel much of problem about pushing to your into your skin, that kind of pain. Okay, you don't have it. Okay, so remember, pressure is actually force, total amount of force applied over the cross perpendicular area or cross sectional area. Okay, so since that's the ballet dancer, okay, so I got to whatever have a toe, okay, on the floor. Okay, so this is the toe on the floor. So what is the pressures at the toe there? Okay, so it is the force is the whole body's weight, right? The force is the whole body weight, and area is just the toe area. Okay, so it's mg over s. I think they say the shoes in the contact with the ground is s. Okay, so g, so mg is the weight of the whole body, and then that is the area. So answer is D. A truck moves so there's a velocity along a straight road. A car and kinetic energy is equal to is moving along the same road. The mass of the truck is the mass is again the 4 times of the weight of the car. Okay, so that means this 4m. Okay, so this is m. What is the speed of the car? The speed of the car is actually equal to, they are equal. So I have the car and I have the truck. Okay, so car and the truck the kinetic energy is the same. Okay, so the formula is always half mv square. Okay, half mv square. Okay, so I have 10 meter for the truck. I do the truck first. Okay, so if the car have the mass of m, then my truck have 4m. Okay, so they give me the number already. Okay, so half so the truck is half time 4, half time no half time 4m, not very good. Okay, okay, is half time 5,000 times 10 square. 10 square is 100. 10 square is 100. Mass is 5,000 and got to half it. Half it means 2500. 2500 and another 20. So the truck have 2500 and another 20. Okay, this is half mv squared. Okay, for this amount. Okay, so this car got to have the same amount of kinetic energy. Okay. Okay, so same amount of kinetic energy. So the speed of the car is okay. So he has an energy of half time mass. Mass is actually 1/4 of 5,000. 1/4 of 5,000. So it's 1250. Okay. So then I have a v square. Okay, I want to find a v. Okay. So this is got to equal to this. Okay. So calculator. 250000 times 2 divided by 1250. 1250. Okay, then take a square root of it. Take a square root of it, also 20. Okay, so 20. Answer. Box slide down slope force of friction of 12 Newton is added on the box as shown this way. So how much work is done against the force of friction as the box move from point P to Q? Point P to Q. Okay, so this is if you want to care about it, the forces. These are frictions. I have a weight. I have a normal reactions. Okay, I have 3 of them, and seems like it is sliding down. Okay, sliding down. So the friction is not enough to balance the these directions, the left lower corner directions of the weight component. Okay, so if you resolve them, that will be the amount of resultant force that will travel in this way. Anyway, okay, so how much work is done against the force of friction? So when they say force of frictions and work done equal to force times the distance at the same direction. So work done of anything is the force of anything, the distance along the anything. Whether against anything is the force of anything and against the force and the same distance. Okay, so blah. Okay, so that means whatever you talk about the work done, you use the whatever the force, and you got to get a distance move along that force. Okay, so these three things are all together. But just now I'm talking about the resultant force that will slide down. Okay, resultant force causes acceleration, so it slide down. Okay, so that will be the resultant work done. Okay, become kind of a loss of potential energy, become gain in kinetic energy, that kind of things. Okay, don't care about it, but because we talk about frictions. Okay, so we talk about frictions, I'm going to say work done against frictions, work done against friction, frictional force, distance along the friction. Okay, so three things. So if I have friction of 12, it's 12, and the distance it move is 5 meter, 5 meters, right? And this distance is exactly the distance that it move along with the frictions, and that is the work done against frictions. Okay, so don't need question too much. 12 times 5, 60 joule. Okay, so this is the answer. Okay, so this is the idea. Okay, when things are getting complex, stick to the formula, and you just keep telling yourself work done against which force or work done by which force is always equal to that force time that force move directions. Okay, so your object move the directions, right? Okay, choose the distance that you move along with that directions. Okay, if it's something else, then you resolve it until only getting that components. Okay, normally your syllabus should be simple. Okay, so you will not need to resolve. Okay, so that's the frictional force, and that's frictional force, and there's a direction it go. That will be the amount of work done against the frictions. Okay, so it will be correct. Okay, so stick to the formula. Okay, let's have a stop here. I think it's a dinner time. Thank you. Okay, testing. Okay, okay. Yep. So sorry, okay. I've just come back. Okay. So I think not ready for my dinner anyway. Okay. Let's carry on. Okay. Which statement explain why a liquid has a fixed volume? I know it's a bit clumsy because I tried to explain a little bit here and there. Okay. So ping me if you want something faster or explain more. Okay. On the other hand, you can also leave a message if you want to. If you leave a message, on anything you want me to go through again, I can go through again. I even go through the whole topic if you make another video. Okay, don't worry. Okay, so which statement explain why a liquid has a fixed volume but a changeable shape? Okay, the idea is that liquid, right, actually is having particle that in between the particles, right, they actually touching one another. They're very close with one another, but they can slide along each other. They can slide along, but they cannot leave gaps. Okay, so that's why liquid can actually all the particles can slide until like any shape that they want. Okay, but they cannot compress because they are already packed. Okay, so there's no air, no gap. Okay, but air, right, it will be like they are all distant away from each other, so they are quite loose to one another. So you can compress them, and they can also repel each other, but in with a distance. Okay, so that's why those are the air. Okay, so for solid, they can't even slide at all, so they cannot move. It's rigid. Okay, so there's a free idea. Okay, so molecule means the particles. Okay, molecule. This word is in chemistry. Okay, it doesn't matter. Are close together. Yes, it's either close or together far apart. This far apart, it can be compressible. Okay, fixed volume means that it cannot be compressed. Okay, compress them, you also will not reduce the volume. You release some air pressure or just make it more vacuum. You also cannot tear them to be a bigger size. Okay, so that's why it could be close together and are changeable shape because they can slide along one another. Okay, so move over each other. This is the right. Not vibrating in fixed positions, right? This is solid. Okay, this is solid. Okay, so this is liquid. This is solid. Far apart can move away from each other. This is gas. Okay, far apart fixed position. This is weird stuff or something is not in syllabus. Don't care about it. Okay, so answer. I think it is A. Okay, answer is A. Okay, so it's here. So next one quickly. Okay, the diagram below shows the liquid being heated. Beep, beep. Okay, this is beaker. This is liquid. This is heat. Okay, what happens when the liquid at the bottom of the beaker? At the bottom of beaker will get heated. The liquid inside here will be heated, and we know this is about convection, con radiations and convections, and the first one is what conduction. Sorry, that's very old stuff. Okay, so this liquid, so liquid conduct heat via convection mainly. Okay, it can have some conduction, but it's very minor compared to convection. So we not mainly talk about liquid is convection, solid they cannot run around. Okay, like the particle can swim around or slide along with each other. Okay, so they can do conductions. Okay, so when you have a color, okay, those will be radiations. Okay, so like radiations of the light, you feel hot when your hands is a little bit away of the fire, because those are radiations. Okay, so nothing that's through the air or through the vacuum also can get you hot. We feel the sun is hot. Okay, this is also radiations. Okay, so that's actually the medium is actually air or vacuum. Okay, so this medium is about, but air with smoke you can also treat it as a fluid, so it also can do the convection. So it makes sense for you to really feel that it's directly shine to you, then you garner the heat. Okay, that will be radiation. Or you will feel that is it some wind that blowing some moisture air that you feel hot, or are you in the kitchens that actually your soup are being boiled, and and then the some water vapor come out the time you just feel like having some hot breeze, this kind of thing. Those will be counted as convections. Okay, so even though you are in the kitchen there, it depends on what you feel. Okay, so that's actually from different sources, they are all coming together. Okay, so be careful, this is convections. Okay, when the liquid at the bottom of the beakers get heated, Okay, get heated, what happened? The density will be lesser. Lesser density rise. It rises, right? Okay, styrofoam rise. Okay, so that's why the hot liquid will go up, and then the cold one will come back here, so that you have a complete convection current like that. Okay, so then the liquid will decrease and then it will rise. Okay, so the answer is A. Water can change state by evaporating and boiling. Yeah, both correct. Okay, water can change by evaporating and boiling, but evaporate, right? Evaporate. Okay, evaporate only take at the surface there. Okay, it's like you if you how am I going to do? Okay, anyway, it will just keep on uh disappearing at the surface. Okay, so this one will get removed. This particle will go out first. Inside, right? Inside the particle will not will not cause evaporations. Okay, they will not get evaporated. But boiling is everywhere. Okay, it's nearly all are boiled together. Okay, that's what we learn. Okay, so it's like you're boiling the water, you see the bubble everywhere. Okay, evaporation only evaporate on the surface. Okay, so you're covering the surface, right? Then nothing get evaporated. Okay, so only occur at the surface is evaporations. Okay, boiling actually is everywhere, but only occur at one temperature. That is boiling. Okay, or only at the boiling point. Okay, evaporations can do at any temperature. Okay, any temperatures, how cold it is, it can still evaporate. It's just a more evaporation or less evaporation only. Okay, they will still undergo evaporation. Okay, so answer C. Diagram shows a wave for the surface water, ripple dam, water, vibration up down the wave, the way travel left right. So this is a trans longitudinal. This is a transverse wave. Yeah, sorry. Oh, this is very old words. Okay, transverse wave. Okay, so the wood rod generate a ripple of 20 vibration in 10 seconds, 20 vibration in 1 second. What is the speed of water wave? Okay, so while we off this information, okay, this is 1, 2, 3, 4, 5 lambda. Okay, 5 lambda equal to 6. Vibration 10 vibration 20 vibration in 10 seconds. 20 vibration in 10 seconds means your t, okay, period is number of oscillations per unit time. Okay, so like that. Okay, so equal to 2 hertz. I'm sorry, not 2 hertz. Okay, 2 second. Frequency is equal to 1 over period, so frequency is half. Okay, so half hertz, 0.5 hertz. Okay, so and this 5 lambda, right, means your lambda is equal to, but lambda is in meter, cannot be in cm, but they make cm per second. So cm per second, that means your speed also using cm. So let's just follow cm per second, and this in second, right? I'm sorry, this is in hertz. Hertz is reciprocal as second. Okay, so this is called uh hertz. Hertz actually is 1 over second. So actually it's second minus 1. Okay, so it's okay. So we have formula v equal f lambda. V equal f lambda. So the v we lost the speed that we asked is this value. Okay, so I need f times lambda only. Okay, so my f is from here, which is half, and the lambda is 6 over 5. 6 over 5. Okay, because 5 lambda equal to 6 cm, right? So in terms of cm, I have my lambda equals 6 over 5. So it's 6 over 5 times 1 over 2. Chuck chuck. 2, so it's 3 over 5, make it decimal. Okay, so times 2, so it is 0.6. Answer is B. Okay, what is equal to the period of water wave? What is equal to period of water wave? Period is the time for one complete oscillation. Time for one complete oscillation. So period is a time. Okay, so careful. Okay, distance between the bye bye. The time for the water surface at one place to move from its maximums to minimum. From maximum to minimum. Here. this is to here. So it's actually half oscillations. One complete oscillation is the time for down and then up, back to up. That will be one complete oscillation. Okay, so this is wrong. The number of wave passes upon in 1 second. Number of wave passes upon in 1 second is like it's like how many wave in 1 second. Actually, it's actually frequency. So this is actually frequency. But anyway, this is not the time, it's number of wave lah. And the unit will be per second. So certainly it's not time. Okay. So this is wrong also. Okay, the time taken for the peak of the wave to move the distance equal to 1 wavelength. Okay, so this is actually, this is correct. Okay, but why is it correct? Because we talk about a wave. Okay, for the peak of the wave here to move to here, the time is exactly when this. So after this guy moved to right side, you see this guy move to this side, right? Okay, so in order for you to see a phenomenon like that, okay, that means I will see a guy like that and this guy take over kind of things, right? So this guy move down and up again will just be one wavelength movement. Okay, one wavelength movement. Okay, so that's why answer is D. Okay, so the time for it to move from here to there or from here to there is the same as the time for it to go down and up again. Okay, so answer is D. Okay, so next question, 16. A sound generator makes a musical note of a single frequency which a person can hear. A sound generator, blah blah blah, a single frequency which a person can hear. So audible range, right? Which change make the sound generator give a quieter sound of a higher pitch. Okay, so quieter sound means that the amplitude, that means the maximum swing of the wave. Okay, the more, the louder. Smaller, softer. Okay, higher pitch means the frequency. Okay, higher pitch means frequency increase, amplitude decrease will be quieter. Okay, so you know pitch, right? Pitch means the sharper like girl sound like that, and lower means the guy sound like that. So that's actually frequency. Loud or not loud is due to the amplitude. Okay, and then one more actually is called quality. Okay, quality actually is the signature wave style of the wave, the pattern. Okay, like signature like that. Okay, they have a repeated section of for some ugly wave like this, right? It will sound like something. Even they can be in same pitch and in same amplitude. That means same softness, right? A guitar playing that note and a piano playing that note will be different. It's because the waveform is different. Okay, the form is different. That's what we call the quality. Okay, so it's all about amplitude, frequency, and quality. Three things. So anyway, quieter amplitude decrease, higher pitch, frequency increase. So here and here. So answer is B. Two resistors of electricity. Two resistors series are connected to 12 volt supply. Wow. Okay, two resistors in series. Okay, those in series. So check the battery first because the battery will be the one that drive the current. Okay, something like the water pump will start to press the water to flow. Okay, so it is positive here, it's a negative here. So current will flow from positive like that, go over to negative. Okay, so in the beginning it's like that. Okay. And a third resistor connected to the circuit below. Okay, so effective resistance of a circuit, what happened? Okay, so before that, okay, effective resistance of a circuit is increase or decrease. Okay, so it's before and after. So we talk about before, we talk about after. Okay, so before it is your whole water pump is pumped in this way, right? Go through in there and come back to the pump here. Okay, so that's why it's in two series. Okay, series resistance you just add. Okay, so the total resistance total will equal to 20, which is 10 plus 10. Okay, so after, okay, you join this, your water will pump in this way and come to this junction. It will split to both. Okay, and then it will join back to here. Okay, so this guy is parallel to this guy, and this combined guy will be series with this guy. Okay, so the whole effective resistance, we do the parallel first. Parallel, how to do? Okay, okay, I use the traditional formula. Okay, resistance total equal to 1/10 plus 1 over 10, okay. Okay, so 2 over 10, 2 over 10, so the resistance is actually 10 over 2, so it's 5, okay, so this guy effective become 5 ohm, got it, okay, so 10 ohm plus 5 ohm, so resistance total equal to 10 plus 5, 10 plus 5 equal to 15 ohm, so from 20 to 15 it decreased, okay. In general rule of thumb, you can have a quick one, okay, this is a MCQ, right, okay, so any parallel guys, right, any parallel guys, whatever value it is, I put 1 million on here. So long as parallel to this, the effective of this, right, will be lesser than any one of them. Okay, so will be lesser than 10. Even this guy 1 million will drop until 9 point something. Okay, so they will become 9 point something. Anything parallel will reduce the resistance. Anything you chuck in series, you increase the resistance. You talk about increase and decrease. Okay, so I know in the beginning I got one guy series with this guy. So this plus this. Now this guy, because of this guy come in, the overall resistance here decreases. So this guy plus this guy now is naturally lesser. So straight away you know the actually is decreased. Okay, you don't have to do a calculations. MCQ what? Okay, you don't have the value, right? Okay, when the whole resistance decrease, what happened to the whole current? Because in the whole thing that remember circuit, okay, in circuit the current resistance don't anyhow work, okay. It's always the potential difference. That means it's always the voltage drive the current. Okay, the current big or small is due to the how much voltage you apply. This is the cause. This is the effect. Okay, so this is the driver. Okay, when you drive this in the circuit, and if your circuit with any resistance, then the resultant current will flow. Okay, you will put a battery there. The battery actually guarantee you the potential difference only, and the whole is just like the pump can only give you the pressure, high pressure, low pressure, or water pressure. But your pipe is flowing through on whatsoever configurations, then you start to have the water current flow. Okay, so current is the end result of a potential difference or voltage. Okay, so we fix the potential difference first. Okay, so that means, right, if I have same potential difference here, or same battery here, the potential difference is guaranteed unchanged. Okay, this is the standard things about battery. A battery is fixed in potential difference, and currents, how much it will flow, is depends on your resistance, or is it a complete circuit. If it's even broken circuit, no current can flow. The potential difference will still guaranteed. Okay, you still have plus minus 5 up here. Okay, if the things just cannot flow only, but this is 5 volt, then this is 0 volt, so there will be a difference of 5 volt. Okay, difference, potential difference. Okay, battery guaranteed potential difference. Okay, so when my battery don't change, you add Harman resistance, I still have the same amount of voltage there. Okay, so voltage is always the same. Okay, or we talk about EMF is the same. Okay, because the battery never change. Okay, so now my resistance decrease, so my current go higher. Okay, so current will go higher, and my EMF is guaranteed unchanged. That's the things about battery. Okay, so remember, it's the EMF or the potential difference of the battery will dictate. Okay, okay, the whole circuit flow. Okay, so or rather it will just drive the circuit to flow with current. Okay, the current is the result of applying potential difference. Okay, so it's not another way around. Okay, there's always one cause, one effect. Like Newton's second law also, it's the resultant force that will drive accelerations. Okay, it's never on the other way around. Okay, so that's why acceleration is never any. The direction of acceleration is always the direction of resultant force. Got nothing to do with velocity. Okay, velocity is velocity. Acceleration is from resultant force. Okay, always think about resultant force. Then you got give you acceleration, and acceleration give you change in velocity. The velocity kind of affected by acceleration. Okay, so the force will give you the acceleration. So this always, and the velocity will give you the distance change, right? The increase in distance and all these things. So that's the cause and effect in physics. Okay. Free resistance in circuit, wow, which is so resistant, got so many questions. Okay, so 2. Okay, got 2. Okay, so be careful. Okay, I got 3. This is also electricity. So I think electricity, good chapter. Okay, guys, be careful. Okay, the free resistor in the circuit is this. In this way, the resistance each resistor is 20 ohm, 20 ohm, 20 ohm, 20 ohm. Okay, 20 ohm, 20 ohm, and 20 ohm. 20 ohm. The reading of the ammeter is 200 mA. What is the reading at the voltmeter? okay, never mind about it, okay, get voltmeter. Voltmeter means this means what's the potential difference, right? I know this is fixed, okay, but I don't know what is the value, right? It's not given, okay? So 200 milliampere flow through here, okay? So that means the current flow through the resistor is actually this amount. 200 milliampere equal to 0.2 ampere, okay? We use ampere, okay? 0.2 ampere and this 20 ohm. So V equal to IR 0.2 times 20. So actually it's 4, right? So this is 4 volt. Okay. So that means this is the amount go through the resistor, and this is the amount go through resistor. This is the resistance. So that's the potential difference across the resistor. So this is actually 4 ohm here. 4 ohm across here. Okay. Ammeter assume is just wire. Okay. Voltmeter just assume to be a broken circuit. Okay. So these two are just as good as broken. So nothing will disturb your circuit. Okay. So have it or don't have it is the same thing. Okay. So 20 across this resistor is supposed to be across here and here. Okay. 20. No, actually it's 4 volt. Okay. 4 volt across here, and this is distance y. So that means 4 volt across here. So that means this point and this point is 4 volt, right? 4 volt. So how many volt is here? Okay, so we can calculate a lot of things, but there is a trick for this. So if this is 20 ohm and this is 20 ohm, the effective of the resistance here is how many ohm? Okay, it's actually 10. Okay, otherwise you can just do 1 over 20 plus 1 over 20 and 1 over, okay, you will still get 10. You can do that, okay? But I know that if the same resistor you put parallel, it's just half them. You put three of them, one third of them. Okay, so it's just like that. Okay, so and then now this combined is 10 volt, that's 10 ohm. This is 20 ohm. So the potential difference, right? Because V equal to IR, so I equal to V over R. Okay, the I through here will be the same I through here. Okay, so the I through here is the same I through here. So when you have a resistance, okay, the resistance you have is actually inversely proportional to the uh, uh, potential difference. Okay, or no, it's proportional to potential difference. Okay, so that I keep my I the same. Okay, so okay, having I the same, IR V, you know, if this is constant, because pass through here, same amount, right? So the R is proportional V. Higher the R, higher the V. Okay, so it's 2 times 1, so it's 2 times 1. Okay, so 20 ohm to 10 ohm, 20 ohm to 10 ohm, then I will have 4 volt to 8 volt. Okay, that means my battery is actually 12 volt if you want to. Okay, 8 volt. Okay, so this is my answer. Okay, so if you have a problem on this, okay, we can do a very detailed calculation. Can, no problem. Okay, 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 let's just let's just delete this. Yeah, okay, so then okay, so okay, so if you want to do it again, okay, just let me know. Okay, leave a comment. Okay, yeah, okay, so this watt is power. Okay, it's used a factor of 30 minutes each day. It actually costs 24 cents for kilowatt hour. What's the cost using the heater each day? Okay, each day, what's the cost? Money. Each day. Each day means 1 day, but each day 1 day means use 30 minutes. 30 minutes means that in our standard unit, okay, so means 30. No, okay, that's in joule. but the cost got to be in kilowatt hour. 30 minutes. Okay, so kilowatt hour. Okay, let's change. How will okay, I think I know how to do. Okay, of course. Okay, but let me see how I'm going to present easier to you all. Okay. Okay. Hopefully this is okay. Come back again. So easy. Okay. So what's the cost? I want money. Okay. So the money is actually from here. Information. Okay. 24 cents per kilowatt hour means that every 1 kilowatt hour is you will need 24 cents. Okay, so everything in cents, huh? Okay, so I will got that means I just need to ask how many kilowatt hour I use, right? Okay, so it says 1 day. 1 day means 30 minutes. Okay, so this is time in 30 minutes, but my unit is in the hour, so this is 0.5 hours. So that's the hour I have. Okay, so power of this electric heater, it is 80,000 watt. So how many kilowatt? Okay, so take out 30, so it's 80 kilowatt. Okay, how many kilowatt hour I've been using is just how many kilowatt times how many hour. So it's actually 80 kilowatt times 0.5 hour. Okay, that will give you 40 kilowatt hour. Okay, so 1 kilowatt hour is 24 cents. So 40 kilowatt hour I use for each day is actually times 24. So it's 40 times 24. 40 times 24. 40 times 24. 960 cents. Okay. $9.60. Okay. So okay, 960 cents. Okay, 20. Electric kettle has a metal case. The live and neutral wire are plugged of the kettle connect correctly, but the earth wire is not connected to anything. There are no other electric fault. What happens when the kettle is switched on? Okay, so electricity current come from live and into the heating element and to the neutral, and they say correctly, so it will work. Okay. Then supposedly the earth wire, what's the use of earth wire? Earth wire is to anti or short, right? Don't get electric short. Okay, should be this kettle. So sorry, okay. My mouse is just like that. So it's to prevent people from getting electric shock when we touch the casing of the appliance in case the live or neutral part, any part of the complete circuit, live in, neutral come out, the one, okay? Live in, heating element, heat hot, okay? Then go out, okay? That's the neutral one, okay? Then anywhere got electricity and if it touches the casing and you go to touch the casing, right? Then the live power will go to the casing and then come to execute you, and then uh yeah, okay, so you just go to the ground. Okay, so then you get electric shock. Okay, and even though if we go to the heating element, after that go to neutral, the neutral cannot touch the the casing, right? It might also have a smaller amount that go through you, also will not be good. Okay, those are electricity. Okay, so the earth is where have a competitions should connect to the touchable surface. So in case anything happen, the earth wire will conduct away most of the electricity. Okay, you will just feel nothing. And the earth, once the earth have current, your power box will trip. Okay, so this is the mechanism for that. Okay, so that's due to the earth. So normally when nothing really happen, your earth shouldn't have any current. Okay, when you have current, then the power box will switch and the electricity given will be switch off. Okay, so those are electricity leakage. Okay, so but then if this is not connected to the casings, right? Once you touch the casing, if there's anything wrong and exposed to the surface, you get electrocuted. Okay, so not very good. Okay, so but it will still work. Okay, it will still work because all you need to work is that the live heating element go back to neutral and the things will get boiled. Okay, so this idea. Wiper will switch on and it will boil off. Okay, so it heat up normally. It will heat up normally also. Okay. Fuse in the plug will melt. This will not melt. Okay. will not melt, okay? Because melt means that excessive current flow through more than the desired amount of current flow through the wire. Remember just now what I said, okay, is the potential difference or the EMF or the source voltage, right, is actually driving the current flow, okay? So when they drive and the current go excess, okay, then the fuse will melt. Okay, fuse is for excessive current one. Okay? It's not for earth wire kind of things. Okay, so if this question is about earth wire, it's not testing on that. Okay, so this is not the one. Okay, so it will heat up normally, and the kettle does not become live, provide no other fault, but the kettle becomes live and dangerous to touch. Okay, so best answer would be C. Okay, because okay because they're not supposed to touch. But the point is that what if inside the water is also somehow conduct electricity to the outer surface of the kettle, and what if there's no insulation, all these things. Okay, so better answer than that. Okay, okay. So answer C should be the one because the kettle does not become live. What's the meaning of kettle become live? Okay, like biohazard like that. Okay, no, what it means is it the live wire electricity can go to the kettle surface. Okay, the kind of thing. Okay? Help the teacher. I think it's very poorly written. Okay, so anyway, C. Okay, this is what your syllabus. Okay, so just answer accordingly. Wire accordingly. Good thing. So this is about the physics first part. Second part, carry on. Hot water from the kettle is poured in the glass of beaker and the room temperature. State what happened to the molecule of the glass beaker as the temperature of the what beaker increases. It's a keyword. State what happened to the molecule of the glass beaker as the temperature of the water, is it? Okay, let me go to find out the book. Physics. Blah blah. Long question. Question one. Of the glass beaker increases. Okay, so this is glass. Okay. What happened to the molecules of the glass beaker when hot water is pouring inside? Okay. So this is beaker and the hot water going in. What happened to the molecule inside? Okay. So the molecule itself, right? So before and after, right? So will the glass melt? It will not, right? So it's from solid remain solid. Okay. So the molecule of a glass beaker, okay, is still remain a solid state. So it has. We talk about the what happened to them. So we'll talk about those kind of explanations. So for all the solid particle, we will have vibration and rotations. Okay, it will not have translations. Okay, so it cannot slide along with each other, and the density will still be in their position. So the molecules will still be in their positions with vibration and rotation. In the syllabus, I think only vibrations. Okay, they don't care about rotations. Okay, but actually we know vibration, rotation, and translation. Translation means go away already. Okay, those are for liquid and gas. Okay, so that means the glass will still remain a glass. But secondly, but it will vibrate and rotate to me, okay, more violently because you increase in temperature, right? Increase in temperature means the molecule move more violently. Okay, so the vibration get more violent. Okay, so the idea I think I just put vibrations, uh, vibration get more violent. Okay, vibration increase. Full stop. I think this is what they ask. You can talk about this. Okay, and rotation don't care. There's no translations. Okay, so you can talk about remain whatever. See how many marks he has. 1 mark. Okay, 1 mark. I just don't care. Vibration increase. Okay, that's it. Very soon, the outer surface of a glass beaker is too hot to touch. Explain to a molecule how energy is transferred from the hot water to the surface of the glass beaker. Okay, hot water to the surface of glass beaker because the hot water, as the hot water touch the glass beaker, okay, the hot the hot water transfer heat to the glass beaker via conductions. Yes, conductions. Okay, I know you will be tempted since it is liquid, right? okay, you tended to use convections. Okay, but remember convection talk about the convection current. That means when the water are drifting among the water due to heat. Okay, those kind of things called convections. Okay, but we talk about the water to the glass. That this is not this 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 spot. Okay, this spot when you pour the water inside a glass. Okay, the glass spot here getting hot is not due to convections, right? It's not due to the convections. Okay, you don't convect already, then I got hot. Okay, if you talk about you pour your water inside here, and this space is too hot to touch. Might due to the convections. Then later the hotness come out. Okay, but I thought all your water are hot. Okay, so the way that is because it get hot immediately mainly is due to it touches. Okay, the liquid touch the glass get hot. Common sense, right? So I will choose wire conductions. Okay. Okay, or rather it says the outer surface of the glass because it's too hot to touch. Okay, so I was let me complete the whole thing. So the water to the inner glass, okay, is due to conductions. Okay, and the inner glass wall to the outer glass wall, hot, right? Because they say outer surface. Why they say outer surface? Okay, so within the glass of the glass wall, from the inner to the outer, the whole thing is solid. Okay, so solid to solid is conductions. Okay, for sure. Okay, so you can say that the vibrations getting more violent from inner molecule that will actually causing the vibrations that next to it. Okay, uh, uh, particles, okay, will get hotter also. Okay, so the vibration will it's like the violent vibrations behavior will actually affect the adjacent particle all the way until external glass area. That is actually the conductions in terms of thermal molecular theory. Okay, so up to you to roughly answer in this way. Okay, I think you should get a very high mark. Okay, I think N level don't expect too deep. Okay, so just use the word conductions. Yeah, wire conduction I think is good enough. Okay. Small metal cylinder force are placed on the roller. The small metal cylinder with this placed on a ruler. Diagram shows the cylinder on the rear view from above. Okay, above. The cylinder is now placed on horizontal surface resting on the one of the circular face. Determine the pressure of the horizontal surface due to the cylinder. Okay, horizontal surface. So this is the surface. Okay, so pressure, right? Pressure equal to force divided by perpendicular area. Okay, the force this guy put on the plate, so it will just exert the pressure at this surface. Okay, on a particular area. So what is the force that is actually adding on it? Okay, so in this general way, we'll just say it's the weight. It's the weight of this guy. Okay, so weight equal to mg. Okay, they already give you the weight. Okay, so 7.7, no need to calculate. Okay, 7.7 Newton. Ta-da! Okay, so we find the area. Area is a circle. Okay, so this is the area. Okay, area is this. So I have what I have. Do I have the what's so ugly the marking? Okay, I think is this is in 1 cm. This is in 2 cm. So 1.67, 1.7 marking. Okay, I'm going to find a diameter. Okay, don't look at the one that which is tangents or actually the most the furthest away that it is like the cutting the marking line. Okay, so don't look at the one that is actually inside. Okay, so this one is very weird. So don't bother count 1, 2, 3, 4, 5. I think it just it's the fifth mark. So it's the fifth mark here should be 5.5 cm. Okay, 1.7 cm. So 5.5 minus 1.7 is for 3.8 cm. Okay, so 3.8 cm will be the diameter. Okay, diameter. So area equal to pi r square. So r equal to this one divided by 2. So it's 1.5 plus 4, 1.9 cm. 1.9 cm, so pi r square is pi r square is actually pi, okay, 3.14 blah blah blah, pi times 1.9. 1.9 got to divide by 100, okay, in order to get the SI unit meter. Then you can use the pressure Pascal, okay. Okay, so I have um 1.9, sorry, 1.9 square times pi. Oh, where's my pi? Okay, 1.9 1.9 square. No. Sorry. 1.9 divided by 100. Okay, so an icon meter. Okay, then square it. Okay, so r square. So time pi. Time pi. Okay, so this is the area. This area, right? So force times distance. Force times the force divided by area. Memory in. I don't know how to do memory in. Delete all content. Copy. Okay, good. I think I copy. So I have force, which is 7.7, divided by pace. Can I control V? Yeah, can. So I have 6789.4, 6789.4, 3 sig fig, 3 sig fig, or 4. I got to leave in 3 sig fig, right? Because this is not, okay, 3 sig fig. 769 0 Newton, 3 sig fig. Okay, this is quite sickening. Okay, so this is not Newton, it's Pascal, sorry. Pascal, PA. With figure 720 with zero power, this is supply of calculated current and P equal to VI, power equal to V times I, power 720 equal to 230 times I, so I equal to 720 divided by 230, okay? 720 divided by 230. 3.13, so it's 3.13 ampere, 3 sig fig. The refrigerator is plugged into the main socket, fuse or plug available at okay. Suggest a value rating for fuse plug, okay, it will be 5 ampere. Okay. Even though you calculate exactly 3 ampere, do not use the 3 ampere fuse because this value of fuse is the exact value that it will blow. Okay, so if it works properly in 3 ampere, you use the fuse 3 ampere. When 3 ampere are properly working at the time, my fuse blow already because I blow at 3. Okay, so remember, you always need a fuse that which is higher slightly and the least you can. Okay, so this is the one. If I got 3.5 ampere will will be the correct answer. Okay, but the best one here among here is already 5 ampere already, so choose a 5 ampere. Okay, it will certainly be correct one. Okay? Fuse is must be done in this way. Okay. The center of gravity of a meter rule. Center of gravity is the distance 50 cm. Of course lah. Yeah. Okay. Meter rule is that means it's uniform lah. Okay. 50 cm means the halfway point. Okay. State what is mean by center of gravity. Center of gravity you have definitions, right? It is a point where all the weight is added at. Okay, the kind of things. And or you can just say by having by counter the weight, countering the count by countering. Okay, but okay, just say what you want first. Okay, center of gravity is at the point where all the weight of the object is at the end. Okay, but I will always say that by counterbalancing the whole weight at that specific point, the whole body will be in equilibrium. Okay, so it's actually wise you can use a one finger to balance the book. That will be the point of center of gravity. Okay, something like that. Okay, but my sentence doesn't matter. Okay, follow your textbook one. The diagram shows the meter rule on the length of this and overhanging at the edge of a bench. Center rule, meter rule, bench, and this at 0.2. So this is 0.5 mark. So this is 0.3. Okay, you see everything. The apple is placed at the rule and rule apple together and now shows slowly move to right. The center diagram shows the way of the apple is a particular distance. At this position, the rule is about to tip. The weight of the apple is 2.5 Newton. 2.5 Newton. What's the questions? The questions is the next page. Really? The questions next page. Sigh. The moment of weight of the apple is about the age of the rule is about to tip. About to tip, right? This kind of about to tip kind of things is that means it's the last instance that is about to turn. That means it's still just nice that it's yet to turn. Okay, so treat it as still the last instant of the equilibrium. That means you don't have any other kind of normal reactions. The weight is just enough about to toggle about the pivotal point. That means the point of toggling the kind of things. Okay, so anyway, they say that the apple is about. Okay, so first, okay, to answer these things, okay, first you see this. What is about to talk over? What is about being rotated? The apple? No, right? It's the ruler, right? So it's all about the things about ruler. That means I'm talking about the moments of the rulers, the clockwise, anti-clockwise, and about turning point. And when it's about to turn, is it turning about here? No, okay? It's turning about here, right? Turning about here, okay? Because when the ruler turn the time, this is the edge that will turn. So we take moment about, so everything about with respect to this end point. This is the last point of contact. After that, this will toggle over, and then the whole thing will be dropping here, right? All these things. So this is the last instant that the anti-clockwise and clockwise will be balanced. Okay, so the anti-clockwise here is given you that the moment is the apple moment is 2.5, so 2.5 Newton, and this is 0.12 meters, so the moment is 0.12 meter. Okay, so this is the point of the pivot. The second, the weight that is going to counter this is going to toe over is because of the weight of the ruler. Okay, so the weight of the ruler is at the 0.5 point. Okay, 0.5 point. So if this is 0.1, this is already 2. So this is here to here is 0.3, right? Okay, because this 0.2, the whole thing is 0.51. The whole thing is 0.5 here. So with this 0.2, this to here will be 0.3. And you take another 0.12, so this is what you have. The distance is equal to 0.3 minus 0.12 is 0.18. Okay, so this is the 0.18 meter of this weight against the toggling point. Okay, so this time the weight you have is 0.18 times weight will be the clockwise moment about this toggling point, and this apple will be the anti-clockwise moment. It will be this amount. Okay, which is 0.12. This is the one, and 2.5 is the weight of the apple. Apple, 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 Apple. Here, 2.5 here. Okay, so 2.5 times 0.12, 0.3 Newton meter. Okay, that will be the anti-clockwise, and the clockwise also got to be 0.3. 0.3 Newton meter. It's written. Okay, so I don't have to write again. The distance to the center of gravity, blah 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 blah. Back to the second diagram. Distance is what I found already, is which is 0.018. Okay. So the weight of the ruler is the W. Okay. So the idea is that the 0.3 we have is equal to 0.18 times W, because the counter clockwise moment got to be balanced with the clockwise moment in the last moment. Okay. So W equal to 0.3 divided by 0.18. Okay. 1.67. Okay, so 1.6736 Newton. Okay, so that will be the weight. You talk about how many gram, then how many kilogram, then you divide by number one, that kind of thing. Okay. Okay. A ball of the model clay has a mass of 0.2. So answer any two questions. A ball modeling clay has mass of this 0.2 kg. A student hold a ball model clay over an edge of a balcony at a height above the ground 0.7. But you never tell me this student how tall eh? Never mind. I think I treated the balcony together with the boy's hand, and the exact height is actually 7 meters. The unit mass of the kilogram, the unit mass is the kilogram. Okay, the unit of the mass is kilogram. Sorry, the unit of weight is the Newton, of course. Okay, so one other way in which the mass differ from weight. Okay, mass got nothing to do with weight. What? Okay, mass one and other way, or that means the unit are different. This one, right? Okay, they're actually unrelated things. Okay, so you gotta say weight is the product. Product means multiplication. Okay, product of the mass and energy. So not energy, gravity. Okay, gravity. My mouse cannot write. Okay, so is the issue is the G. Okay, so another way is that the weight is equal to the product of the mass and gravity. Okay, so therefore when the for same amount of mass, right, with under different gravity, the weight will be different. Okay, so weight will be different. Okay, so I answer the question like that. Okay, or you can say is that when the okay, you can say that for the same mass, okay, under different gravity, that means different planet, the weight will be different. Okay, Earth and Moon is 1/6. Okay, but no one care about it. Okay, because I think it's 1 mark. The gravitational field strength is 10 Newton per kg, 9.81. I can never hear 10 kg Newton per kg. Actually, it's 10 meters per second square. Okay, never mind. Same thing. Calculate evaluation potential energy of the ball measured from ground. Now, gravitational potential energy GPE is actually equal to mgh. Okay, mgh. Is it weird? No, mg is the weight, right? Height is where the weight move along. Actually, it's work done against gravitational force. Force times distance is the same thing. Okay, so why are we remembering this formula? But we get used to it. Mgh. Okay, so mgh. So mg is already 10. I'm sorry. The g is this is g. The m is 0.2. The h is 7. So this whole thing is 0.2 times 10 times 7. Okay, 0.2, this 2 become 2. 2 times 7, 14. 14 joule. Okay, I don't know whether got joule behind you don't have to put. Okay, the student released the ball and accelerate toward the ground. State the meaning by accelerations. Acceleration is the increase in velocity. In this case, okay, actually it's just the change in velocity. Change in velocity means over time. Okay, we need time. Increase in velocity over time. In this case, is accelerating. Okay, from you release the time, velocity goes 0, and when it hit the ground, it's the fastest. Okay, if you can't imagine, just imagine you are the ball is being released. Okay, you will be able to get it. Okay, so increase in velocity over time is actually the definition of acceleration. Okay, so state what is mean by that. Okay, accelerations. Okay, so but in general, acceleration means the change of velocity over time. But change of velocity, be careful. Velocity got speed and directions. Okay, so change of velocity or increase change of velocity can be change in speed, can be change in direction also, can be change in speed and direction also. Okay, so be careful when something spinning on in a circle, even though the speed is constant, the direction keep changing. Okay, at any moment the direction keep changing. Okay, it's actually having accelerations. Okay, so remember, okay, so it's not just speed, it's velocity. This must answer velocity. Acceleration must answer with velocity. This kind of definition things once you choose the wrong word, the whole mark is gone. Okay. As the balls fall to the ground, the size of the acceleration decreases. Size of the acceleration decreases. This is weird. State one reason. Okay. Suppose if your ball fall to the ground, okay, so it's actually the weight mg, right? And there's no other dangling things. If there's no other force, just purely mg, it will just fall to the ground with a constant acceleration. Constant acceleration means your acceleration is constant. It's always 9.81, and then your speed will go faster and faster and faster until you smash on the wall or smash on the floor. Okay, smash on the wall. What? Okay. So, but why is it decreasing? Is decreasing means some other forces are affecting this mg. Okay, one of them is a drag force. Okay, it's air resistant force. We call it drag force. Okay, in your syllabus it's called air resistance. Okay, so when the air resistance is there, okay, it depends on how many mark. I don't see again. If you 1 mark, you just say air resistance causing the accelerations. Because acceleration is resultant force. Resultant force is this force minus this force. Okay, so when I have this guy, my acceleration is lower than g. Okay, if 1 mark, you just answer this way. But if it's 2 mark, you answer a little bit more. Okay, because the drag force itself, air drag force, is proportional to velocity. Okay, or the speed. Okay, is proportional to speed. Okay, so the point is that when it's you dropping down the time, right? And in the very beginning, it's only have mg. Okay, mg equal to ma. Their accelerations, right, is purely equal to g. So it just fall at 9.81 accelerations. Okay, that means you start to accelerate. In the beginning, you release your ball, got no speed. Speed equals 0. Okay, so now you have accelerations. Okay, and then you start to increase your speed. But once your speed increase, you cause your drag force to increase. So your resultant force equal to ma, force equal to ma, which is equal to mg minus drag. Your drag is proportional to velocity, so I just call it kv. Okay, your velocity, okay, proportionality. Okay, so when a is proportional to b, a equal to kb, that kind of things. Okay, so just now was 0. So the g equal to a. Now you have some speed. Okay, let's say 5 like that. So now kv now is no longer 0. So that means your effective a, right, is lesser than g. Okay, so that's why your acceleration decreased. Okay, the idea is that because drag force is proportional to speed. Okay, when your speed increase, the time your drag force increase, causing your acceleration to decrease. But you're still accelerating. You're just accelerating lesser and lesser until acceleration also goes to 0. You reach your terminal velocity, which is damn fast. Okay, so this is the whole free fall with air resistance concept. Okay, so just go to free fall chapter with air resistance. Go read up. Okay, that's what they want to explain. Okay, above fall to the ground and stop moving after it hits the ground. Describe the energy transfer that take place as the ball hit the ground. Okay, the ball hit the ground. Okay? That means it does not bounce, right? It does not bounce means that it is not elastic. Now we learn about elastic body. Okay, if a ball is perfectly elastic, making a super bouncy, ideal or perfect kind of bouncing kind of material which is doesn't exist in the world. Okay, you should lose the kinetic energy and it bounce back the same height. Okay, there's no loss, right? So less ideal means the practical, like let's say a tennis ball also quite bouncy, so it will just impact and lose some energy and then it will come back here. Okay, so what does that mean? Loss become what? Okay, some energy will become heat and sound. Okay, heat and sound energy. Okay, so kinetic energy loss, potential energy loss become kinetic energy very fast and very fast up. But this value after bounce is already lesser than the hitting the ground. The one because some are lost to heat, some are lost to sound. You hear the bouncing of tennis ball on the ground. There's some sound. Okay, so those energy also counted. So you got lesser energy now. You cannot reach the same height. Okay, so you keep bouncing, 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 bouncing. This is the one. Okay, but it doesn't bounce, right? Stop moving after it hits the ground. Means once it hit the ground, it remain at the ground. It don't bounce. It just don't move or don't roll anything. Just like that. Okay. So I think it is become splashed. Okay, or just stick to the ground. Okay, because it don't move means it cannot move. Okay. Describe energy transfer take place in the balls as the balls hit the ground. As the balls hit the ground, you have all the potential energy in the beginning, okay, all the before release become the kinetic energy at this moment. So from the maximum amount of kinetic energy, when the ball smashed to the ground, okay, it turns to heat and sound and the deformations of the solid. Okay, the major things is your formation is a clay, right? Yeah, it's a clay ball. Clay ball clay ball, okay, clay ball. Okay, so I think I think if it still remains a ball, more or less it'll bounce a bit. But they say totally not bouncing, it got to be like mud like that. Okay, so you smash on the ground, so it deforms, right? It deforms means there is a work done on deformations. There is some work, there's some energy loss on heat and sound. Is what we say. And this is a very extreme case. So the energy will be lost in all these three environment and they become no potential energy and no kinetic energy. Okay, so the PE in the beginning, I have no kinetic, it's not moving, all will become the kinetic energy at the last moment and will smash the ground and become heat, sound, and deformations. Okay, deformations. Okay, remember deformation takes energy. Okay, not yet. Okay, still not yet, Martin. Hi. The distance between the Earth and Moon can determine by sending bright red light from the Earth. Equipment of the Moon reflects the light back to the Earth. Sorry, I think I should still check a little bit on the YouTube. See if anyone have any questions. I did not put any. Okay, very quick one. Let me take a look. Okay. No, 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 no. Okay, I can't read it. I can't read my own channels live. Okay, this. Okay, part two is here. Channels live. Okay, okay, nobody is leaving comment, so I think it's good. Let me quickly finish. Okay, I still got to pass it to my student. Okay, good. Okay, so the distance between the Earth and the Moon can be determined by sending bright red light from the Earth. equipped on the moon reflected the light back to the Earth. Okay, never mind. Okay. Light is in transverse waves. Take one other example of a transverse wave, X-ray. Okay, light ray is one of the visible regions. Okay, X-ray, gamma ray, radio wave, microwave, all these things. Okay, choose anyone. Or water wave, also transverse wave. Okay, so it's up to you to choose. Timer is switched on the same time. There is a vacuum between the surface of moon and moon. Set the speed at which light travels the vacuum, which is speed of the light. So it's 3 times 10 to the power 8. Okay, this is a number got to remember. Okay, the light in return the 2.5 seconds after it's sent from Earth. Okay, calculate the distance between the surface of Earth and the surface of Moon. Blah. Okay, so speed equal to total distance over total time taken. Okay, so distance equal to distance equal to distance distance. Okay, distance equals the speed times time. Okay, sorry, 3 times 10 to the power 8. Maybe here 10 to the power 8. And then time 2.5. Okay, so just choose the 3 times 2.5, which is 7.5. So 7.5 times 10 to the power 8, right? But actually, like that, right? From the Earth, you shoot to the moon, you come back to Earth, right? Bounce in this way. This is 2.5. So you got to divide by 2 to get the distance. Otherwise, you got 2 times the distance. So actually, divide by 2. Okay, ugly number. Okay, 3 times 2.5 divided by 2. 3.75, so it's 3.75 times 10 to the power 8 meter. Okay, that's the distance between Earth and Moon. When the light reflected from Moon and received on Earth is less bright than was sent, suggests which property of the light wave has changed. Which property of the light wave has changed? Less bright, right? Less bright is just like the sound wave, less loud. Okay, it didn't change the color, so the frequency no change. Okay, so frequency no change. Velocity will not change the speed of light, so the only thing change is the v equal to f lambda, v equal to f lambda, v equal to f lambda. Lambda cannot change also because the color and frequency is the same thing. Frequency cannot change. Okay, so velocity don't change. Okay, nothing to do with that. Okay, so what change? Amplitude change. Okay, that means your amplitude. Okay, amplitude change. Amplitude decrease. Okay, why is that so? Because you lost energy. Okay, because when your beam in one way, it has some spread or some where reflected the time you might not reflect totally, that kind of things. Okay, so the energy might be weakened. Occasionally, blue light is used instead of red light. The wavelength of the blue light is smaller than the wavelength of the red light. Yep. Okay, frequency higher. Okay, so explain how the frequency of blue light compares to the frequency of blue light compares to higher law. Okay, red light. Okay, so your wave v equal to f lambda. Okay, v is constant, right? Speed of light is constant. So when your lambda blue is smaller, your frequency higher. Okay, so that my speed the same, right? Okay, so that's why it's like that. Okay, so yep, frequency higher. So suggest checking the result by repeating experiment using what light instead. Okay. So suggest checking the result by repeating experiment using sound wave. Now, sound wave jialat liao. Sound wave instead of light. Explain why the result cannot be checked using this method. Because sound wave, right? Sound wave cannot travel in vacuum. Okay, sound wave need a medium. Okay, vacuum means no medium. No medium wave can travel normally. It's only electromagnetic wave. Okay, any mechanical wave like sound wave, okay, it can't travel without medium, okay, in vacuum. So it cannot travel in medium, full stop, okay, because sound wave is just like a group of choir people singing choir, then swing left, right, then the first guy hit the second guy hit the third guy, the kind of things, right? Then you, as if your wave propel from left to right, the kind of things. Okay, so you need the guys there, okay. When there's a vacuum and nothing vibrating, so it cannot transfer a sound wave. Okay, so that's the idea. Just simply say cannot travel in vacuum. It's good enough. It needs a medium. So sound wave is travel faster in water. Okay, that's what we know. Okay, because they're more packed to each other compared to the sound air. Air particles are further apart. Okay, so that's why all the things. Conductor X is a cylinder, blah blah. Okay, conductor X is a cylinder straight. Conductor X cylinder straight. Usually conducting modern clay. Conducting modeling clay. Clay again. Electric circuit. Make of conducting modeling clay. Okay. Conductor. Okay. This is here a conductor. Electric circuit consists of a battery, a conductor X, and an emitter in series. Okay. Done. Shows terminal. Two circular faces are terminals. Okay. The electromotive force EMF of the battery is not shown. That means how many volt here is not shown. It's a EMF. Okay. State what's mean by the electromotive force. Electromotive force is the potential difference given by a battery that drive the circuit or drive the current flow through a circuit if you want to. Okay, and otherwise you can follow your text. Okay, so electromotive force is the potential difference by the battery that drive current flow through the circuit. Okay, actually potential difference is just it maybe by the battery is good enough. Okay, the current don't mention, because what if the circuit is broken? Okay, circuit is broken, then no current can flow, but the potential difference will still be there so long as you have a battery there. On the diagram, draw the circuit symbol for a meter that is measuring the EMF of the battery. Okay, so the battery, so I just have a voltmeter here and tag exactly at the battery there, be very gassy. Okay, then I will be able to read the EMF. The reading of ammeter is 0.08 ampere. Calculate the charge that passes through the ammeter in 15 minutes. Okay, so current to charge. A current actually is defined as the amount of charge flow per unit time. Okay, so I need to charge. So Q equal to IT. Okay, M 0.08 ampere, and the T is 15 minutes. So 15 times 60 seconds. So 0.08 times 15 times 60 seconds. 72. Okay, so 72 coulomb. Okay, coulomb. Okay, I think I remember the charge is in coulomb. So little, yeah, makes sense. 0.08. It is very little. 0.0, yeah, 0.08 ampere. No problem. The resistance of conductor is 57 ohm. Conductor X is removed from the circuit, and all the conducting model K is used to make a second conducting cylinder Y. The length of Y is double the length of X. Determine the resistance of Y. So conductor X just now was 57. Now I might use the same thing to make the conductor Y. Same cylinder. Double the length. Okay. If you use the same amount of clay to make your resistance Y, that means the volume is conserved, right? So my X, okay, let's say I have okay, my Vx equal to Vy, okay. So my Vx, right, is actually the length X times the cross-sectional area of X, right? Then equal to be equal to the length Y and the cross-sectional area of the Y, because V volume is equal to length times area for cylinder, right? Okay, area, length, and the volume. Okay, so this is something like that. So my length Y is double of the length X, so this is actually 2 length X. 2 length X, same volume. So what happens is that my area X cancel. So length X cancel. So I have my AY, right, is actually equal to half of area X, half of area X. Okay, so that means my length double, my area got to be half. Okay, so we know that resistance equal to resistivity rho L over A. Okay, rho L over A. So my resistance X equal to rho L X and AX. Okay, so your resistance Y is rho L Y over AY, but Ly is actually 2 of Lx, right? But my A, right? The area Y is actually, we know area Y actually is half of area X. Therefore, I have 4 times of rho Lx over Ax. Okay? So that means I have 4 times of resistance of Rx. And the resistance of this is actually 57. So my answer is 4 times 57. 228. My answer. Okay. Conducting cylinder 1 is now connected to a second in series of battery, and calculate the new reading on the ammeter. New reading on the ammeter. So now, because my the circuit is the same, okay, but now this is replaced by Y already, okay. So the potential difference V is the same, okay. This is the battery, right? The battery guarantee is the same. How much current will flow depends on resistor, okay. So just now it flows, which is like 0.08, okay. So V equal to IR. Just now the V cost 0.08. 0.08 ampere to flow. But now my battery is the same, so the V is actually the same. But my resistance, right, actually is 4 times. My resistance is actually 4 times, right? We know that 4 times. Resistance is 4 times. My potential is the same. My current got to be 1/4. Okay, so its answer is 0.08 divided by 4. 0.02 ampere. That's my answer. Done. Oh, that's all on paper. Okay, thanks for watching. Okay, give me a like and subscribe if you want. Okay, then I'll be having my chemistry soon. Okay, and then we just try to do as many paper as we can before the N-level examinations. Any questions, just drop a comment there. Yeah, take care. Okay, we'll see you again.